Welcome to day 16. Homework you got packet page 7. So on the first one, we had started the other day with 1 over 1 minus x and saw that that was really our geometric sum formula. So that was just 1 plus x squared plus x cubed and so on. So if you have 1 over 1 plus x, you've subbed in a negative x for that, so we get the alternating signs. If we want x over 1 plus x squared, well, now we're subbing an x squared in for all the x's. That's what we have in the parentheses. And then to get the x on top, we got to multiply by x. So if we do that out, we only want till the third degree, so that would just be x minus x cubed. In number 2, we want to approximate cubed root of 10. Something nice close to that is cubed root of 8. So we're going to use 8 as our center, and we'll have f of x be cubed root of x. They wanted us to do a third degree, so we got to do 3 derivatives of cubed root of x, and you see those 3 derivatives there. Then we've got to sub in 8 for x and find the value of each of those derivatives at our center. That's where we get the 2, the 1/12, the negative 1 over 144, and the 5 over 3456. So then we can build out our Taylor polynomial. So our original function value over 0 factorial. That's where we get 2 over 0 factorial. Then you have plus your first derivative value at the center over 1 factorial times x minus our center raised to the first, minus our second derivative value over 2 factorial, x minus our center raised to the second. Similar idea for the third. I just neaten that up a little in the next one. And now to get your P3 of 10, that's saying using your third degree polynomial and evaluating at 10, just put in 10 for all the x's and you get the value that is written there. And then if you compare it to what cubed root of 10 actually is, it's pretty close. If we wanted a better approximation, we could add more terms. They give us an equation to find our derivatives for any value of n, and it's non-negative. That means we could use it for 0 also. So put in 0 for n to find your original value, you get back 1. Put in 1 to get your first derivative at x equals 2, you get 3/4. Put in 2 to get your second derivative, you get 1, and put in 3 to get your third derivative, you get 27/16. And we stopped there because they wanted a third degree. So then we just build it out. So we have our original value over 0 factorial, plus our first derivative value over 1 factorial times x minus our center of 2 raised to the first. And then do a similar idea for second derivative, third derivative, and then I just neatened it up there in that bottom line. So they gave us a third degree Taylor. We're centered at -1. And we want to find each of the following or tell that it can't, we don't know. Well, our original term, the 2, is really f of -1 over 0 factorial. Well, because 0 factorial is just 1, that means f of -1 is just 2. Our coefficient of the next one, the -1, that's equal to our first derivative at -1 over 1 factorial. Well, because 1 factorial is just 1, the value of our first derivative at -1 is just -1. F double prime of 0, notice they've switched the center. We can only find our values of our derivatives at -1, so C we can't determine. And then D, our coefficient, the 12 is equal to our second derivative at -1 over 3 factorial. Well, 3 factorial is 6, so multiply it over, and we get 72 must be the value of the, oops, that should be third derivative there, is the value of the third derivative at -1. For 5, we've got our original value, we got our first derivative. And if there's an inflection point at x equals -3, that means we know the second derivative should equal 0. So this would be our second degree setup. But because we had a 0 for the second derivative, the second degree term doesn't show up, so you just have 8 plus x plus 3. All right, so we wanted in 6, we want a local minimum. So we know then that f prime should equal 0. If it's a minimum, that's in a concave up section, so we know f double prime should be positive. So we're looking for a choice that does not have an x to the first term, so that rules out these. And then we want the second derivative to be positive, so that would have to be choice C. In 7, notice on the graph here, at x equals 2, f of 2 is 0, so we should not have a constant term, so those are gone. F prime of 2, we are increasing, so it should be positive. Both b and c have positive coefficients for our to the first term. And our second derivative, it's a concave down section, so that should be negative. So it's got to be choice B because the coefficient of the second degree term should be negative. In H, we want a second degree, so you have your original, you have your first derivative, you have your second derivative. It's Maclaurin, so we are subbing in 0, and we get our original value, first derivative value, second derivative value. It's x minus 0 for each of them, so we end up getting this in terms of k for our second degree Maclaurin. Then in 9, we're going to use that for different values of k. So really we've got k as negative 3, so just fill negative 3 in for k and you get that second degree polynomial. And in b, we really have k as 2/5, so you get that second degree polynomial. In C now, we've got the square roots. We want k to be negative 1/2. So fill in negative 1/2 for k, and that's what we would have for 1 over square root of 1 plus x. But we want 1 minus x squared, so replace all your x's with negative x squareds. We get this, but then we just wanted second degree, so we'll just take it up to there. Now, 1 over radical 1 minus x squared, its antiderivative is arc sine. So you can do your antiderivative of that Taylor polynomial. We get this with a plus c. We know arc sine of 0 is 0, so that means our c is 0, so that's gone. So we get this here, but we only wanted second degree, so we drop the third term, and up to the second degree would just be x for us. All right, so our topic for today is Lagrange error bound. It tends to be a challenging topic, so we will spend 2 days on it. So an idea with Taylor polynomials is they approximate our functions. So if you have a fourth degree Taylor polynomial for cosine there, cosine of 1/2 is approximately what we would get when we sub in 1/2 for that fourth degree Taylor polynomial. So it's an approximation. How do we know how good that approximation is? We would want to be able to find the remainder. So what is basically the difference between the actual value and our approximation? In this course, Lagrange remainder is a technique that we use to find that. So the Lagrange remainder theorem says that our remainder is our next derivative at some value of z over our next term factorial, n plus 1, and then this is some value minus the center raised to the next power. So like if we had a 6 degree polynomial, those n plus 1s would really be 7s. So we do the 7th derivative. Now what's that number z? Well, z is some number on your interval between your center and where you're approximating. So like this one here, this is the Maclaurin, so our center is 0. We subbed in 1/2. So z would have to be some number between 0 and 1/2, and it could include 0 and 1/2. Well, how do you find the z value? Often it's impossible. So the best we can do is pick an upper bound for it. So what we'll do is we'll pick a value on our interval that's going to yield a y value of that next derivative that will be an upper bound on the interval. That's the idea of it. So what we'll often use in that spot is a capital M. What capital M represents is the upper bound of the next derivative on our interval from our center to wherever we are looking at. The other parts, again, this, if you have a 6-degree polynomial, that'll just be 7 factorial because it's the next factorial. That would be raised to the 7th. This will end up being the value of our interval where it goes to, and this is our center. So again, we're just finding an upper bound, something nice for that value of m. So we're going to do a 3rd degree Maclaurin for sine, and we're going to use it to approximate sine of 0.5. Well, sine is odd powers, so we're going to have p3 of x is equal to x minus x cubed over 3 factorial. We'll do p3 of 0.5. Well, that's equal to a half minus an 1/8 over 3 factorial, which is a half minus 1/48, which would give us 23/48. So that's our approximation for sine of a half. The idea is, how good of an approximation is that? We would want to do our Lagrange error bound. So we know, some things we know with our Lagrange error bound if we just did a 3rd degree polynomial. We know for our remainder that we're going to have 4 factorial down here. We did 3rd degree, so that factorial should be the next factorial. We know our power is also going to be 4. Those two things will always match. Well, we were doing sine of 0.5, so we'll have 0.5 minus what our center was. We were Maclaurin, that's why that center is 0. The big decision we have is, what is that value of m? M should be an upper bound on our interval of 0 to 0.5. Well, and it should be on our next derivative, I should say. So on our 4th derivative. So we need to think of the 4th derivative of sine. What is an upper bound on 0 to 0.5? Well, the nice thing about sines and coses is their derivatives are always plus or minus some sine or cos. And they always stay between -1 and 1. So for sines and coses, the easy thing to do is just always make that m value be 1. So for any value of t in there, that max value is 1. So we can just use 1 for that value of m. Now remember, m is a magnitude, so we always put in a positive value for it, even if in that next derivative you would get a negative value. So if we sub this in, we're going to have a half to the 4th, which would give us a 16th. And then dividing by 4 factorial would give us 1 over 384. So that means we know sine of 0.5 is our approximation that we had minus 1 over 384. It's greater than or equal to that, or less than or equal to our approximation plus 1 over 384. So we can be confident that sine of 0.5 is in between there. Now you will often see those fractions not combined. You'll see them separate with the subtraction and the addition, so it is easy to identify the approximation and the remainder value in that. Now you might be saying, well, why pick 1? We could have been even more accurate. So if we think about it, x equals 0.5 is less than pi over 6. because 0.5 is 3 divided by 6, and pi would be 3.14 divided by 6. So we really know, so basically pi over 6 would be about here. And we know at pi over 6, that should correspond to a y value of a half. So we really could have said that we know that, and I should specify that we know our fourth derivative here is sine specifically, not cos. If it was cos, we would need to think about it a little differently. But our fourth derivative, which is our next derivative, is sine. So we could have used a half for our value of m. So all that would have changed for our remainder is we would have had a half over 24, and then we would have had absolute value of that 0.5 minus 0 to the fourth. And I should specify that 24 is coming from the 4 factorial. And if we did that out, that would give us 1 over 768. So we then could say that we would have that 23 over 48 minus 1 over 768, and 23 over 48 plus 1 over 768. So it's not necessarily the point to find the smallest value of m. We want something that's just definitely going to be an upper bound and is reasonably small. So you don't want to say, okay, we know for certain that that fourth derivative of sine is definitely going to be less than 1,000,000. Let's put 1,000,000 in for m. Okay, so usually you pick the next nice number above what you know the max value is. That's usually the technique. But by thinking about it a little more, we said it could have been a half. Now what we'll learn tomorrow in tomorrow's video is how these tend to show up on the AP. The AP exam doesn't want some people picking 1 and some people picking a half. So they'll word the questions in a way that forces everyone to pick the same value of m. Today we're just wrapping our head around on where that m is coming from. So we'll have options and we'll actually pick what that value is. If we move down to the bottom, we're going to do a fourth degree for to approximate the cubed root of e. Keep in mind that's really e to the 1/3. So we're going to have p4 of x. Remember, e is all positives, has every power and every exponent. So that's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. If we sub in a third to that, and just evaluate it on your calculator, you would get 2,713 over 1,944. Well, let's see if we can pick out a value of m for that. First off, we know, let's see, this is supposed to say a 4 here, because we want our fourth remainder, because we were doing fourth degree in this case. So our fourth degree remainder at a third, some things we know for certain is this factorial has to be 5. In our absolute value, we should have the value we subbed in minus the center is Maclaurin, so that's 0. And then this exponent should match that factorial 5. So the decision is the m. So e to the x is an increasing function. So 0 to a third, well, think about what e to the 1 is. E to the 1 is 2.7 and change. So we could be confident by picking 3 for m, because we know 3 is a nice number bigger than e to the first. So therefore, e to the third we know is something less than that. Now I should specify, we are looking at e to the x because that's the fifth derivative of e to the x. It just happens it's the same as the original function e to the x, but we're really looking at it as it's the fifth derivative. Because it won't always, that next derivative won't always be the same as the original function. E's, sines, and coses are pretty easy. But say we had something like 1 over x, you would have to do out 5 derivatives and then think about on your interval what would make it, what would be the upper bound of that. So this is our fifth derivative e to the x, and an upper bound on the interval that would be nice would be, we know 3's got to be bigger than it. So if we fill 3 in here, and we sub that in our calculator, we would get 1 over 9,720. So we know cubed root of E is between 2713 over 1944 minus 1 over 9,720 and 2713 over 1944 plus 1 over 9,720. Well, you might be saying, we could have done better than 3. So cubed root of 2.7, 2 cubed, 2 times 2 times 2 is 8. So cubed root of 8 would give you 2 back. So cubed root of 2.7 has got to be something smaller than 2. So we could have, if we flip to the next page, we could have said, okay, we know that E is less than 3, so cubed root of that has to be less than 2. So another convenient m we could have used was 2. So all that would have changed, we would have had 2 over 5 factorial, absolute value of the 1/3 minus 0 to the 5th. And this would now give us 1 over 14,580. And again, this is a 4 here, really. So we could write our bounds. Now we've kind of narrowed it even more. We know cubed root of E is between 2713 over 1944 minus 1 over 14,580, and that with a plus as well. So again, as I mentioned, we'll see tomorrow how they give it on the AP. That forces everyone to use the same value of m. But for now, we're picking something convenient that we know is guaranteed to give us an upper bound of our next derivative, in this case, the 5th derivative. We'll say we want our remainder to stay within 0.001. Okay, this is still working off the previous question because notice we're doing the remainder at 1/3. Well, we've got to pick either the 2 or the 3. Let's say we go with the 3. So we know m is 3, but the thing we don't know is how far out do we need to go? Well, this is always the next power in the next factorial, so we can put that in as n plus 1, and we want it to stay below 0.001. Well, if we flip to the next page, what we can do is we can do this in a graphs page in the calculator. So we can make a little t-chart. We've got n. This would be our 3 over n plus 1 factorial. Absolute value 1/3 minus 0 raised to the n plus 1. Now, when we put it in a graphs page, we will need to put those in as x's. So we'll go to our graphs page. We'll do our fraction button. We've got 3 over. Make sure you do the x plus 1 factorial in parentheses. I should say put the x plus 1 in parentheses and then put the factorial afterwards. Now, we don't necessarily have to put in the absolute value because 1/3 minus 0 is just 1/3. So we'll put in 1/3 and then we'll raise it to the x plus 1. So then we would go Control T, and if n is 0, we get back 1. If n is 1, we get 0.166. Well, we want to be less than or equal to 0.0001. Well, this one is 0.0015. Now, you got to be careful in the table. It'll switch you to scientific notation. Notice this is 10 to the negative 4. So that's really 3 zeros and then a 1. So that's going to be our first one that works for us. So if we copy the table over, at 0 we had 1. At 1 we had 0.166 and change. At 2 we had 0.018 and change. At 3 we had 0.00115 and change. And at 4 we had 0.000102 and change. So the first one that is below 0.001 would be the 4. Now, when you are doing these, you need to think to yourself, does our Taylor polynomial for what we're working with have all the degrees? E does, so we can look at each of them. But if we were looking at a sine, we would want to only look at the odds in our table. If we were working with a cos, we would only want to look at the evens in our table, because those Taylors only have those certain degrees. But E has every degree. So, because we put it in as n plus 1, that means n is the term that we would want to go out to, because the n plus 1 then was the next term. So this would say that we need a 4th degree polynomial. And if it's 4th degree, we started with n equals 0, so that means it's 5 terms. Be careful, sometimes the questions will ask each of these. What degree polynomial do you need? Or it might say, how many terms do you need? So just be careful of the difference between those. Now, if we had done it with m equals 2, so we would have had we would have had 2 over n plus 1 factorial and 1/3 minus 0 to the n plus 1. So we would have gotten 0 equals 0.6 repeating. We would have gotten 1 equals 0.1 repeating. We would have gotten 2 is 0.012. 3 is 0.00102. So that still wasn't enough. 4 was 0.00006. So we still would have gotten that the 4 was the same one. Okay, so that won't necessarily always be the case that it'll be the same if you pick a different m, but in this case it was. So again, the big idea with these ones is only look at the terms in your table that would be in your Taylor polynomial. E had every power, so we can look at all of them. If we were working with a sine, we would only look at the odd values of n. If we were working with cos, we would only look at the even values of n. That's it for this video. Have a great rest of your day.